Welcome to DeviceDojo. I'm Joseph, and this is where we tackle the practical side of securing connected devices, from over-the-air updates and fleet management to the broader challenges like incident detection and response, compliance, encryption, and more. Always actionable and hands-on. Brought to you by Northern Tech, the makers of Mender.io. Let's get started. So, you already know that we are doing something really new. This is the DeviceDojo. This is the inaugural first session. And yeah, you might know a little bit about me already. I'm Joseph. I'm the developer enablement expert at Mender.io, product by Northern Tech, which sponsors this whole series. And during the DeviceDojo sessions, well, there will be one general longer streak. Every second Thursday of a month, I will be doing one like tutorial, hands-on, actionable session. But there occasionally will be other sessions too, like tutorials, live codings, office hours, whatever hits my mind, whatever I kind of like feel is valuable to you. So, what do we talk about today? Encrypting persistent data with LUKS and TPM. The first question that we should tackle is, what does persistent data actually mean? And from there on, we'll step through the building blocks until we actually end up putting everything together within a Yocto build, which you can take and use as the base for your own projects later on, because all of the sources of the repository is already live on GitHub. And I am pretty sure that I will mess up the demo at some point in time, but that's what you're here for, right? Yes. Michael, I mean, that was the point of the music, right? So we also have some fancy things you like. You know, whenever you feel like something that I'm doing is worth discussing, just head over to hub Mender.io and drop your questions, comments there. Okay, so first, persistent data. When it comes to connected devices, I would always say not all data is created equally, because you will end up deploying new software, and if you're doing A/B updates, then it means that whatever you have on your root file system is basically transient. A best practice always is to have the root file system read-only, because A, it's more stable, and B, it makes sure that you do not accidentally, because people do not always follow best practices unintentionally, you do not unintentionally drop data that you will need later on the root file system. So you do the update and you wonder, hey, where's my data? So always have a clear separation in your head between the static stuff that does never change during operation. That's the key point, but is transient during updates, and the mutable data that you intentionally modify during operation, like user configuration data, application data, logs, whatever, and put that on a separate persistent partition. I mean, that's required to some degree by default, but the key point here is there's also several degrees of additional persistent data that you might want to adjust to. In this case, we will create a fully standalone persistent data partition that will be fully encrypted upon first device provisioning. We find the next slide. When we talk about transient and persistent data, you might still want to encrypt for data protection, but the reasons are very, very different, because your static data, the operating system, the application, everything in there is boring, if you ask me, because I mean, who really wants to see the umpteenth copy of the glibc, but still there might be your intellectual property hidden in there. This refers to your application code, or eventually any assets like a closed AI model or things like that. If you roll them out with an image-based update, this ends up on the root file system, on the transient data. So if this is crucial for your business model, then you might want to encrypt that. The mutable data, the persistent data, might need to be encrypted for privacy reasons. Especially under the CRA, remember that whatever user data you have, you always have to provide a way for a full factory reset and to make sure that no sensitive data leaks out. The really easiest way to do this is to encrypt the persistent partition, because if you need to do a factory reset, well, then you just erase the key. That means that whatever is on the persistent partition is still there. But without the key, it just looks like random data garbage. And assuming that you've used proper strong encryption, there's also no way to recover it. And the latter is what we will talk about today. Creating such a persistent partition, especially in the context of Mender, is really, really straightforward, because there's 2/3 variables that you need to set, and then the build process adds an additional persistent partition with a known label to your image. This is what we will need later. And for the sake of this example, I'm just using 64 megabytes of fake X4. I mean, the X4 is definitely always just overwritten by the encryption later. So I already told you, wipe the key. This is a little bit of a problem in embedded. Where do you put the key or the password? Because in the most straightforward case, you encrypt something with a password. But most of your devices, even if they hold personal data, you don't want to enter a password upon startup just to make the device functional again. Very good example always is a coffee maker. The coffee maker will, to some degree, hold sensible data if it is connected, like your Wi-Fi connectivity, the counter, blah, 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 blah. But having to enter a password into a coffee maker before you get your morning fix, that's just not very comfortable, right? So the key here are TPMs. TPM stands for Trusted Platform Module, and it is a secure way to store key material which cannot be extracted from the hardware. In this case, we are using, or for the demo, we are using a Raspberry Pi 4. And for the Raspberry Pi family, there's a module that's called Let's Trust. It is definitely not the only one. It is the one that I just happen to have. So check out GitHub, check out the blogs, especially by Leon, for example, who has just recently announced a fully open source hardware variant of this one, which is a little bit more comfortable to slot in, but I just happen to have those ones already. And in the end, they are really, really similar. The key point here is it needs to be TPM 2.0 compliant, and then you can get started. As I said, in our case, the TPM serves mostly as a secure key storage. It can have a lot more functionality, as far as I know. I've only started to scrape the little bit on top of understanding TPMs, but I mean, you can hold key hierarchies to some degree. You can even insert code in there. Thank you, Michael. Let me just add that one here. But one of the strongest and most important functionalities these days is the platform configuration registers, the PCRs. They are thoroughly defined. You can follow the link in the slides. I'll also make sure that this one ends up in the show notes. And the PCR, essentially, there are 16 of them usually. And it means that only if your system at various stages or points of evaluation can provide a specific hash, then the key for decryption or for any other action will be provided by the TPM. In our case, we will be using PCR7, which is defined as holding the secure boot configuration state. Thanks, Michael. It's always nice to have somebody around who does like feed me the stuff that I can show. So next slide goes in here. I already mentioned that there's keys from the TPM and there's a password. So how does this one come together? Because if you encrypt like a zip with a password, then you need to have the password to extract it. If you don't have the password, yeah, well, then you're out of luck. So this is the final building block which we need is LUKS. Linux Unified Key Setup. I'm skimming over the nitty-gritty details here, but the key idea is that you encrypt a block device with a master key, and that master key is essentially still stored on the block device or in its header, and you have additional password slots to unlock the master key. You have to obviously make sure that all of these additional slots are really strongly protected too. But this has the really big benefit that you can have multiple of them without having to re-encrypt the full thing. Because imagine you have a really big block storage device, 10 gigabytes. You encrypt all of this. You encrypt all of this with a master password, and then 1 week later you realize, oh dang, I need to set a new password for whatever reason. My birthday changed, and this is the magic of the master key. The master key should be unique per device, but you can unlock it in various ways. So imagine in slot 1, you have the standard password, your birthday, that I just hinted to, and you add a second slot for your wife's birthday because she should be able to unlock it too. And then you decide like, we're just gonna settle down on my wife's birthday, and then you just scrape slot 1, which means your original password will not be functional anymore. And the other one, your wife's birthday, will be able to unlock it. And you can repeat this as many times as you want. So, yep, there was a question. Can you remind me what TPM stands for? Yes, Trusted Platform Module. There's 2 big generations, TPM 1. something. I think the final iteration of the first standard was 1.4, but it's essentially fixed function and deprecated and dead and don't use it anymore. And TPM 2.0, which is the current iteration and what you essentially should go for. Yeah, another nice pointer. Thanks, David. Actually, yeah, Paul Kissinger is the mastermind behind the Let's Trust module, and I happened to meet him a couple of weeks ago and discussed a little bit on how things progress. He's told me that there's something really cool and up in the pipeline, but I'm not allowed to talk about it yet. So if you're interested in following more TPM news, check out tpm.dev on LinkedIn, because that's what his community runs, and follow him because, as I said, I know that there's new stuff up the pipeline. I already told you that LUKS means you use a master key per device. And that's basically the root of one of the challenges that we face in this demo. Because imagine you want to pre-create the full image, including the encryption on somewhere in your CI pipeline, somewhere on your developer desktop, wherever. Then even if you would add separate slots, the master key would still be the same. So if you roll out such an image, it means that if somebody managed to break the unlock password on one of the devices, they end up being able to extract the master key and therefore are able to scrape the data of all of your fleet. And this is obviously what you definitely need to avoid. That's why you cannot pre-encrypt images for devices like this. The encryption of persistent data needs to happen on not exactly first boot, but upon first provisioning. So when the device either comes out of factory reset or gets unpacked and booted up for the first time, whatever stage you have before the user can add personal data, that's when you have to encrypt the persistent device. And once that is done, the final building block, which we need, so I already told you we have the slots with various passwords, and using the TPM as one of those slots is the key for tying the TPM to the encrypted partition. And so we can automatically unlock on boot. We will use system decrypt and roll. There's a couple of other variants. I think one is called Clevis, and I'm just saying I usually use systemd for stuff that I do. It's working. No bashing here, please. So we have all the building blocks now, and we need to put it all into code that you can actually use later. So the first part, when you want the setup like this, is obviously you have to enable the TPM. And this is where it already gets a little bit icky occasionally, because the TPM is not something where you just like set a flag, okay, give me the TPM. But you actually need to add it to the device tree, which is either a patch to the device tree, or in the case of the Raspberry Pi, because there's a little bit of magic, let's call it magic, in the closed bootloader earlier, which can load overlays. So in this specific case, it's a device tree overlay that gets loaded early in the boot process. Plus, we obviously need tooling to interact with the TPM. We can install that into our image. And the final thing, which I forgot on those slides, yeah, bad me, you also need a little bit of kernel configuration, because otherwise, yeah, it's nice that you have a TPM, but if the kernel and the kernel on the user space doesn't know what to do with it because there's no driver and no modules, well, then it's not a lot of use either. So to just make sure that your TPM is actually working, you need, again, device tree, tooling, kernel configuration. In this specific case, I'm using the groundwork that Claire, I think I'm always getting his name wrong. He's also the mastermind of the Sulco distribution, has done. It's also, again, linked in the source code, which I'll show you in a second. And then you can like boot up and say, okay, TPM, get capabilities, or show me the PCRs. And then you know, okay, the device is actually working. The next building block is encrypting the persistent partition on first boot. And then once you have those two things, then you need to enroll the key into the TPM. So it can actually be unlocked upon boot. And with that, let's look at the code. Demo time usually blows up. I don't think that this will ever change. So that's the way. And give me the code. Device tree overlay, as provided by Paul, Peter, I'm not making this up, and Isa, is it ties the Let's Trust TPM to SPI. So it enables the bus with the according pins, and here comes the module itself with compatibility, TPM2 over SPI. It has an additional reset pin, and OK means, yes, it actually should get enabled here. We need another thing. Let me see. Yes, here is the kernel configuration fragment. You can see this here in Linux, Raspberry Pi configuration fragment. It just gets added in through an overlay, and it essentially enables all of the TPM infrastructure plus a random hardware number generator. This is what you need so the TPM actually works. Already told you we need a couple of more things, especially the first encryption. This is not what I actually wanted. I wanted that one. So I happen to know that the persistent partition will be MMC BLK 0 partition 6. This is statically defined here for ease of demonstration. So this service is meant to run upon startup. It checks, is it already encrypted? If yes, nothing more to do here. We check that the root file system is writable. This might sound a little bit strange here. And this even more. So why do we store a static key on the root file system? Two things. First, of course, I need to put it somewhere for demonstration purposes. But remember things like your master password of Microsoft's BitLocker or something? Just magically encrypting things is nice. But you also, if it is valuable data of the user, you also need to give them a way to extract the data in case the TPM breaks, the device breaks, whatever. So in the standard situation that we have here, the persistent partition is encrypted, it is locked, and it will only be unlocked if the device integrity is not compromised and the TPM is the same, so the key can be provided. But again, assume the user has put valuable personal data in there. They might want to be able and extract the SD card or whatever other form of storage there is and get the data out with some other means like data rescue, whatever. I'm talking about legitimate data rescue here. And for this case, they should be able to note down a password in a secure place. I mean, I guess you know these rescue sheets that you need to print or should print out if you run full disk encryption on your MacBook or on Windows BitLocker or whatever. And this is exactly the same concept. So here I'm just basically doing a very, very simple preparation for this. And that's why I'm writing to root. I could also write to RAM, whatever. But then there should be a really stable process to extract this at least one time for the user before reboot, because otherwise it's gone. So as I said, it sounds strange writing the password to root, but take it as a starting point. There's a question, what could be the persistent partition, OS, data, or both? In this case, we're talking only about data. I talked a little bit about it in the beginning. This is about securing user data. Having an encrypted root partition is a little bit of a different beast. Maybe I'll cover this in a future session. So we've got the key. We create something really, really random, and then the real magic happens. We do crypt setup with LUKS format on the device. We open it. That's important. Just encrypting will essentially write the container. Then you open it. Only if it's opened, you can actually format it. So the encrypted data block holds a file system. Then we get the UUID, the unique identifier of the resulting mapper device. So I guess I skipped over this a little bit. Crypt setup open uses the device mapper functionality of Linux to create a device of this name. So I just happen to know that I'm using static in all of this example. So the static device shows up in devmapper static, and I can format it. I need to get the UUID of this and store it in a variable for now. I close it again. And then I need to still enroll it in the TPM, or I need to enroll the TPM in LUKS. Again, crypt enroll, as already mentioned, for the static device. This just checks, hey, did something go wrong? And if nothing did go wrong, then we insert the password, shred the file. And the final part is we need to also make sure that there is a mount point. Why am I doing this here? This is due to the peculiarity of Yocto and its packaging, that you can't easily have an empty directory packaged up. I could work around this in some ways. I'm just doing it like this here. So I enter the full FS tab configuration here. And that's why I needed the UUID. I want to mount to MNT static. I'm using X4. The rest is straightforward. And then we can reboot. There's the question, if the root is not encrypted, what is the configuration file that references the TPM? Great question. It's here. And that's why I wanted to jump to the encryption script first before looking at it. So let's just take one little step back to the actual recipe, which does all of this. You see that it does not only install the systemd service, it also installs, or the service and the script, it also installs the crypttab. And the crypttab is the final missing piece of configuration, which tells the boot process, triggered through systemd in this case, to eventually do the device creation for this. As I'm a big believer in properly defined dependencies, I'm not just slapping everything into the image recipe. I'm being clear that this first boot init actually needs crypt setup. It needs systemd crypt to do all of the magic, and it needs TPM tools. The rest is just really straightforward, putting this stuff in. And now you might wonder, hey, Joseph, you're already installing the crypttab before the first boot, and the stuff actually is encrypted. Yes, I'm doing that, and it's a little bit of a nasty trick because that results in static just not being properly set up before the first reboot after encryption. And here comes the hopefully, oh, too many open. Where is it? Where is it? Where is it? I hopefully had the systemd unit somewhere. I don't have it. Let me find it. Here it is. And that's the final trick here. That you may not have a dependency on the static service for this device, because otherwise the first boot init, which is meant to actually set up this device, waits for a device which cannot. So you essentially create a loop. And after a little bit of tinkering here, this is the tricks or the proper configuration that systemd needs for actually making sure that you can write to root and to the partition, and the setup is actually not done yet. So it runs one time, it starts this, and once it runs, it has run or executed for one time for good, it creates a marker, and then you're good to go. All of this is also explained in the README, but we're not going to walk through this here, because I would say demo time means that we actually run this, at least for one time. So let me find the terminal. Terminal. Here we are. Come on. At the stage. Yes, here it is. So I could not flash this before, because if I had flashed it, it would boot up and you wouldn't see anything. So flashing here now. Well, this does actually work. Again, remember to check over to head over to hubmender.io, and let me play a little bit with these things here. Wasn't there like, oh, too bad. Like and subscribe. Yes, I always wanted to click this on a real proper live session. Okay, how far is this one? Let's head over to the serial terminal. So you can see this one is still flashing, and once this finishes, we will actually see a boot process here. This is just my leftovers from preparation for the session. Still flashing, still flashing. Even more flashing. I'm surprised that nothing did go wrong yet. Usually something falls over, and I'm 30 minutes in. Nothing bad happened. That's feeling a little bit weird to me. Come on. Should we play more with fancy things here while this actually flashes? Okay, now it's over. We should see the boot process coming up every second. Yes, here it is. And yes, here comes the key type, and reboot. Start restarting the system. Everything is up. Root, mount, and yes, you can see def mapper static is mounted on MNT static. So all of the crypto magic is in place. Does this work? Yes. So it runs through device mapper. We can have a short peek at the crypt setup. No, crypttab. I meant the crypttab. Cat etc crypttab. So it gets noted there, and maybe finally the FS tab. Yeah. So it's there. So that's it for my demo. But now I'm seeing, let me just jump on to the next slide, because I already gave you a couple of ideas what you should add to, if you're doing something like this, a process for the user to have the key properly stored in a safe place, maybe using TMP, not TPMFS, TMPFS for the temporary password, and of course, proper error handling. I'm always skipping this for demonstration purposes. And the source code is behind this link. I'm going to drop it here too. Let me just find it. Where? Yes. Close commands. So source code. Okay. And yeah, the obvious takeaway is that the TPM only locks to this specific device. So it does not protect you if somebody actually takes the whole device and then just boots it up. Because if they just grab the whole device, then they also have the TPM. So if you need to protect against full device theft or whatever, you need to have a different strategy and threat model. And the real big thing is encryption always has to happen on the device in such a scenario. Didn't I have a question? Q&A? Wow, too bad. I need a Q&A slide. So because there was the question, is there a rule of thumb when using a TPM or OPT? In the end, it really doesn't matter, because as long as the API that they expose is good enough for system decrypt and roll, it really doesn't matter. I mean, OPT is in the SOC, which you might want or might not want. So it saves you the cost of adding additional or the resources of adding additional hardware. You don't need PCB real estate, all of the stuff. And I'm hearing good things about it. So I would probably say if it is good enough for what you need, well, then go for it. I haven't heard of any major attacks on OPT or similar strategies, and I would say, yeah, why not? TPM is probably interesting if your device does not, or if your SOC does not have such integrated, or if for whatever reasons you do not want something on your core to happen. I mean, I'm not super familiar with how the scheduling on IMX or on systems with OPT works. But I mean, in the real worst case, you have you have just a single core CPU, and opt is running somewhere below all your stack. So if you're doing crazy stuff, then I think it might interfere, but that's just guesswork at the moment. All I can say is, from what I know, it should be able to fulfill this, and I've heard good things about it. Beyond that, I'm really sorry, I don't know. And as Michael says, yeah, opti does just not exist on all SOCs. I don't know if that applies specifically to the Broadcoms. It is at least not available on the Raspis until now. Maybe Broadcom has hidden stuff in there. They just didn't tell us yet. I mean, I'm pretty sure they have hidden stuff in there, and are just not willing to tell us. The question is, what is it? Yes, and that's it from my side. The next session is planned for October 9th, again, same time, and I want to talk about fail to ban. Everybody knows it from the servers, but I think it is actually a very, very useful addition for your connected devices, and I will tell you why and how you make that work. That's the last slide from my side. Any other questions or remarks before we enjoy the rest of our Thursday? Leon says, yes, there is no opti on the existing Raspis. Well then, thank you everybody for joining me in the first session. Hopefully see you next time around. As I said, we will talk about all kinds of stuff that helps you secure your connected devices. I will always make sure that it is stuff you can actually use the space for your own projects, your own developments. I really want to make it actionable. And yes, Paul, it should already be. It only went to the source code link obviously only went to YouTube, but I'll drop it in on LinkedIn in a second too. Thanks everybody for joining me. See you next time. If you have interesting topics or questions that I should prepare, ping me. And as I said, over on YouTube or whatever, click the like and subscribe so you get notified when I do the next round. And here's one for you, Michael. Wake up again.